Welcome. We shall start today's class by discussing the Saha ionization equation. So, we consider an atom, let us call it X, and we consider a reaction where this atom interacts with the photon which has sufficient energy to ionize the atom, and as a consequence the atom goes to an ionized state, plus and electron. The same thing could also be applied in principle to study the transition from a singly ionized state to a doubly ionized state, etc. So, it is not only for the first ionization, but for subsequent transitions to higher ionized states also. In general, we are going to consider a situation like this, and the question that we are interested in is that if I have the whole thing in equilibrium at a temperature T with certain density rho, then or number density n, then what is the fraction of the atoms that is ionized? And this is governed by Saha's ionization equation, which was worked out first by Saha. Okay. So, we know that at sufficiently high temperatures, in thermal equilibrium, the number density of any species Ni, I here could refer to the atom X or the ion X plus or the electron, not the photon. So, in thermal equilibrium, the number density is given by the Maxwell Boltzmann distribution, and the Maxwell Boltzmann distribution tells us that the number of particles with any specified value of momentum, the number density of particles with any specified value of momentum is given by Gi into exponential mu into mu I into beta into exponential minus mi c square plus p square by 2 mi into beta. So, the Maxwell Boltzmann distribution tells us that the number density of particles with momentum in the range dqp by h cross h cube is given by this expression. Here Gi is the degeneracy of any of these states. So, it is a spin degeneracy Gi. Mu I is the chemical potential corresponding. So, we are looking at the ith species. Gi is the degeneracy of the ith species. Mu I is the chemical potential of the ith species, beta is the same for all of these species, same for the photon, these atoms, the ion and the electron. It is 1 by the Boltzmann factor into the temperature. Mi is the rest mass of the ith species, and I could refer to either the atom, the ion or the electron. Okay, so let me remind you what we are interested in. So we have this atom X, which is in thermal equilibrium at a temperature T with its ion and an electron, right. This is a possible reaction. So if at a temperature T, all these things will be in thermal equilibrium, and provided the temperature is sufficiently high, the number density of any of these species is given by the Maxwell Boltzmann distribution, and the number density is given by this expression. It has the temperature and the chemical potential of that species, also the spin degeneracy. To find the total number density, I have to integrate over all momentum states. Okay. This is basically the energy of the particle into beta, e to the power minus the energy into beta, that is the Boltzmann factor. Okay. To find the total number density of a particular species, I have to integrate over all momentum values. Okay. So this will give me the number density of that particular species, right. And we also know that this integral d cube p e to the power minus mc square into beta is a constant that comes out. Okay, that comes outside the integral. So we have to essentially do the integral d cube p into exponential minus p square by 2 mi kb t. Where I have written out the value of beta, and this is a three-dimensional. There are basically three Gaussians in this, three different Gaussians, each of them being integrated from minus infinity to plus infinity. So each of these integrals gives us a factor 2 pi into this number over here. So mi kb t, the whole thing to the power half is one of the integrals. So here I have a product of three integrals, one for the x component, one for the y component, one for the z component. So we have to the power 3 by 2. So we can just straight away substitute that here, and we get the number density of any of these species to be gi exponential mu I by kb t mu I minus m I c square, where I have taken this factor outside, and then we have this factor over here, which is 2 pi mi kb t to the power 3 by 2. Okay. So, this allows us to write down the number density of each of these species, provided we know the chemical potential and we know the mass of that species and we know the temperature of the entire system which we are looking at. Okay. Now, in thermal equilibrium, the chemical potential of all the species on the left hand side of this equation is equal to the chemical potential of all the species on the right hand side of this equation. We know that in thermal equilibrium this should be true. Further, photons can be created and destroyed at will. There is no conservation associated with photons. The photon number is not conserved. So, the chemical potential for the photons is 0, which essentially tells us that the chemical potential for the atom should be equal to the sum of the chemical potential for the ion plus the chemical potential for the electron. Okay. The second input that is required is the fact that the energy is conserved in such a reaction. So, here if I take the rest mass of this atom and take the sum of the rest masses of this ion and the electron, the sum of the rest masses of the ion and the electron is going to be more than the rest mass of the atom, because the atom is obtained by binding these two together. So, there is a loss of energy in that process, and the difference between these is the energy that is required to ionize the atom. So, if this is the energy required to ionize the atom, this is equal to the mass of the ion plus the mass of the electron minus the mass of the atom into c squared. So, this difference is the energy that is required to ionize the atom, that is the ionization potential delta E. Okay. So, with these two inputs and we have this, we can now take the ratio we can now consider the ratio of the number density of particles in the ion into the number density of particles of the electron divided by the number density of particles in the neutral atom. Okay. So, let us consider this. When we consider this ratio, we will have one factor which is the the ratio of the corresponding degeneracy factors. So, we will have G x plus G electron by G x. Then we will have the ratio of exponential mu by kT for this species into that of this species divided by that of this species. So, since the chemical potential is in the exponent, we will have the exponent of this plus this minus this, which is 0. So, the chemical potential term exactly cancels out from the whole thing. Okay. Now, we have another term which is the mass term, the rest mass term. So, we will have minus the exactly this. When I consider this ratio, I will have another term which is, so I will have another term which is exponential this that is the ionization potential energy, ionization potential. And we have a ratio of this number for the product of this number for the ion and the electron divided by that for the neutral atom. The ion and the neutral atom, the masses are approximately the same. So, in the ratio it cancels out, and what we are left with is oh, there should be a factor of h cube here, which I have forgotten to write down. The h cube comes from the phase space counting, right? You have to count per unit volume in phase space, which is h cube. So, we have this factor 2 pi into m mass of the electron kb T to the power 3 by 2 by h cube. This is the Saha ionization equation. It plays a very important role in astrophysics in a variety of situations. Okay. The ionization fraction, let me complete this. The ionization fraction is the fraction of the total number density that is ionized. The total number density of particles is, so the total number density is nx plus, that is the neutral number density plus the ionized number density, this into the ionization fraction x gives me the fraction that is ionized. Okay. So, we can use this equation to solve for x. Okay. It is quite straightforward. Let me just leave it here for the, or we can, okay, we can, so you can use this equation and solve for x, the ionization fraction. Okay. And this equation has a variety of applications. For example, if you are dealing with hydrogen, let me just look at hydrogen. The interior of the star, we are here interested in a star. So, the interior of the star is initially largely made up of hydrogen. So, if you are interested in looking at the state of hydrogen at a certain temperature, then the spin degeneracy of an electron, we know it is 2. The spin, it's a spin half particle and it has 2 possible spin states. The hydrogen ion is a proton, which again is a spin half particle. So, that too has a spin degeneracy of 2. This is for hydrogen. Okay. And the hydrogen atom, the ground state of the hydrogen atom, there are 2 possible states. In one state, let me just look at that. In one state, the proton spin and the electron spin are aligned. In the other state, the proton spin and the electron spin are anti-aligned. Okay, so that is, now this has a total spin of 0. So, it has only one state. This has a total spin of 1. it's a triplet. So there are 3 possible states. So totally there are 4 possible states for the ground state of neutral hydrogen. Okay. So for the ground state of neutral hydrogen, this is for hydrogen, Gx is equal to 4. Okay. So you can put in these numbers here. The ionization potential for hydrogen is 13.6 electron volts. This we know from atomic physics. So you can put that in here. The mass of the electron is known, and then if you assume that the hydrogen has certain number density, the number density is going to be here, right? There is one number density here, one number density here. It's a number density squared divided by just a number density. So there will be one factor of number density hanging around. So if you assume that you have a certain number density of hydrogen atoms, then you can calculate what fraction of it is going to be ionized. So you need to know the number density n of hydrogen atoms, of hydrogen basically, could be atoms that are ionized, NH, and you also need to know the temperature. Once you put these 2 things in to this equation, it will tell you what fraction of the gas is ionized, what fraction is neutral. Okay. And this is a very important equation. It has a variety of applications, and we shall be discussing another application of this equation in cosmology. But here we have been looking at the star, and the reason why we have been discussing the Saha ionization equation is that we have been looking at the equation that governs the structure of a star. Okay. And the Saha ionization equation tells us whether the gas inside a star at any location is going to be, what fraction of it is going to be ionized and what fraction of it is going to be neutral. Okay. This is important because we need to know the number of particles. If it is ionized, then the number of particles increases, and for the same temperature and density you will have a larger pressure, right. We have seen this. So the pressure at any point is rho kBT divided by mu into the mass of an hydrogen atom, and mu is the mean atomic weight. So for hydrogen, we have already discussed this. For hydrogen, if it is neutral, mu is 1. Whereas if it is ionized, then the mean atomic weight is half. Because the electron has weight approximately 0, the proton has the same weight as the hydrogen atom approximately. So, but the number of particles has doubled. Okay, the number of particles has doubled because we have the electrons and the protons both contributing to the pressure, right. This is actually n kBT. This is the formula which we have written like this in terms of the mass density. Right, the pressure is n kBT, n is the number of particles. Pressure, sorry, by volume. Okay. So the number of particles doubles, and so you the pressure is different. Okay. So when you want to solve for the state of the interior of a star, this is an important quantity that has to be. It also is important at when you want to determine the opacity. Neutral atom will have a certain opacity. The ionized atom, the electron, and the ionized atom will have a different opacity. The electron is after all a charged particle, so it can interact directly with radiation, whereas atom will interact only at certain frequencies corresponding to its spectral lines. Okay. So this is something, the Saha ionization equation is something that one has to solve simultaneously. So, let me now discuss how one goes about solving the equations that govern the stellar structure. Okay. So, how does one actually model the stellar structure? So, we are now in a position to do this qualitatively, at least discuss the whole thing. So, we have already studied the 4 basic equations that govern the structure of a star. We had 4 equations, one equation for the pressure as a function of r, the second equation is for the mass as a function of r, the third equation is for the luminosity as a function of r, and the fourth equation is for the temperature as a function of r. We had 4 equations. The fourth equation we have seen is different depending on the energy transport mechanism. If the energy is transported through radiation, you have a certain equation. If it is transported through convection, we have a different equation, and we have discussed the condition for which equation to be applied, should be applied. Okay, so we have these 4 equations and for these 4 quantities and the corresponding equations. So, we have to simultaneously solve for the 4 equations governing these 4 quantities. In addition, we have to provide the equation of state externally. This has to be given. This has to be solved because the pressure gradient involves the density. So, we use this to eliminate the density from all of this. Right. All of these equations depend on the density, and we can use this relation to eliminate the density and write it in terms of the pressure and the temperature. Okay. We also have to externally specify the energy generation rate epsilon, which we have seen depends on the density, the temperature, we have already discussed this, and it also depends on the composition. This has to be, this equation has to be the how much this is, what functional form it has to be externally specified. The opacity has to be again externally specified, which again is a function of all of these 4 things. The opacity comes in the temperature. The energy generation function comes into the equation for the luminosity. The opacity comes in here when energy is transferred through radiation transport. We also have to specify the ratio of the specific heat capacities externally. So, these things have to be either determined theoretically or experimentally from the study. Say this has to be determined from measurements of nuclear reaction or atomic cross sections. This has to be determined by the measurements of optical cross sections. All of these have to be externally given. Okay. So, all of these have to be given, and once you have this, you have a set of closed equations which you can now attempt to solve. Now, in addition to this, it is also necessary to give boundary conditions if you want to solve these equations. So, you have 4 differential equations, you have to also give provide suitable boundary conditions if you wish to solve these equations. Okay. So, the boundary conditions for a star would be something like this. So, the pressure, okay, first of all at the center of the star, the mass m at the center of the star no the let us see the pressure, okay, the would be 0. The at the center there would be no mass, that is obvious. The mass contained within the center is 0. The luminosity at the center is 0 at the origin. The pressure at the surface of the star should vanish if it has to be in equilibrium. The temperature at the surface also has to vanish. So, one could put in these boundary conditions and you have the equations, 4 differential equations for these in addition to these conditions. Now, what one could do is one could then tell that, okay, so I know the mass at the origin is 0, at the origin is 0, I know all of these boundary conditions. What one would have to do now is that one would have to specify the radius of the star, because which are the points where you want to set these two to 0? One would have to specify the radius of the star, and by solving this equation, these equations, you would get the mass of the star. But that is not typically how one would like to formulate the problem. So, the way I have set it up till now, you would have to specify r the radius of the star and then solve for this, which would give you the mass of the star, which is the m at r. But typically we would not like to specify the problem like this. Okay. So, the problem is reformulated in a slightly different way, the conditions are set up in a slightly different way, let me mention that. So, the conditions are set up so that you can specify the mass of the star. That is how you would like to solve it. So, the problem is reformulated, the boundary conditions are reformulated so that you can specify the mass of the star and the composition. So, this is how we would like to specify the problem. Given the mass and the composition, we would then like to calculate the radius of the star, the size of the star, and various other things, the temperature profile, the density profile, where the energy is transported radiatively, where it is transported through convection, everything else we would like to solve given this. Okay. So, the problem is reformulated so that these two things can be specified. Okay. And the whole thing has to be solved numerically. So, the whole thing then has to be put into a computer and the set of equations have to be solved Okay. So, the whole thing has to be solved numerically. It is not tractable analytically, this exercise. It is a complicated set of equations with various conditions. Okay. So, the whole thing is put in a computer and it is solved numerically. Now, so suppose you take a star of the mass of the sun and you set the solar system abundances and you set the, so the composition you set it at the solar system abundances and you solve these equations, what you would get as a solution would be something that corresponds to the star, to the sun when it was formed. Right, because you have started off with the initial composition of the sun and you set up these equations and you solve it, then people actually are able to reproduce something that people believe is what the sun looked like when it was formed. Now, as the sun burns the fuel, the composition changes, right, the whole thing evolves. So, what happens is there is fuel burning and the composition changes, and one has to take this into account and again solve the equation. So, initially the composition was the same throughout the solar abundance. Now, the composition becomes, so the composition now is a function of R. Okay. And one has to incorporate that. So, basically there is the evolution effect which one has to take into account, right. So, there is evolution has to be incorporated and then you are finally led to a model which is, you expect to match with the sun as it looks now. Okay. Further, one can also carry out this exercise for different masses okay, other masses and other compositions and look okay, so one could vary the mass and the composition and study the structure of stars in general and they study what both things, structure and evolution of stars in general, of a wider range of stars. So, the whole thing is a very intensive computational exercise which is not, I mean it's not feasible to discuss more details of it here. We can discuss the results. Okay. So, there are now currently existing solar models which have been obtained by this process. Okay. So, there exist models of the sun which have been built up like this. These equations solved with the equations for the energy generation through nuclear reaction. So, when you solve these equations, you know in which part of the sun the reaction is taking place, you can predict simultaneously solve for all of these, the kind of reaction, the reaction rates, etc. So, you have now models which are reasonably believed to be correct. These models have been validated mainly against two kinds of very precise observations. One are the solar neutrino observations, the solar neutrino observations probe the fuel nuclear burning which takes place in the core of the sun. Okay. So, they probe a very small region at the center of the sun. Neutrino burn this nuclear the neutrino solar neutrino observations, and these are very precise, though these observations put very precise limits in, give very precise inputs on the model, and the models now are consistent with this solar neutrino observations. Okay. There are another kind of observations which I will just mention here, again a very important field of astronomy. These are helio, this is a subject actually, helio seismology. So, here what is studied is the oscillations are oscillations, mechanical oscillations. Of the sun. The quantity that is studied are mechanical oscillations of the sun. So, it is like something like monitoring earthquakes on the earth surface. So, you monitor the vibrations on the sun, and it can be done by looking at the intensity of the radiation that you receive from the sun. Okay. And this is relatively easier to model than you can. So, this is relatively easier than modeling the earthquakes in the earth, because the sun is made up of simple gas, it is a sphere of gas, whereas the composition of the earth is much more complicated, there are all kinds of rocks, etc. So, the whereas the sun is easier, so it is easier to model oscillations of the sun, mechanical oscillations of the sun, and these observations, the monitoring of the observation monitoring of such oscillations probe the interior of the sun. So, they essentially probe the entire structure. They probe the entire structure of this of the sun, helioseismology. And models of the sun are now consistent with these helioseismological observations also. Okay. And these models predict that I will not go into the details, I have already told you many of the important parameters of the sun in earlier classes, we have discussed in great detail. So, they tell us the temperature of the sun, center of the sun is around 16 million Kelvin at the core, and it falls off as you go outside. Okay, and a wide range of other parameters in the interior of the sun are predicted by current solar models. Okay. the subject of modeling stars has also been applied to different masses and different compositions. So, that goes into the realm of a different subject, which is the study of the study and classification of stars, which is something that we shall take up in the next class. So, today we are going to stop here.